Welcome back. Today we are going to discuss about how to reinforce the quality of the concrete. Concrete is one of the most widely used materials in the construction industry due to its availability, cost effectiveness, and versatility. The evaluation of compressive strength is crucial in ensuring the quality and safety of concrete structures. Already we have discussed enough about concrete and its quality in multiple episodes. So let's straight to the point. In India, the compressive strength of concrete is assessed based on the characteristic strength determined from 28-day concrete cube test. This is actually prescribed in IS 456. However, there is no universal method for evaluating compressive strength, and the current approach relies heavily on assumed standard deviations and acceptance criteria, which is given in the standard, that lack a strong statistical basis. I took one research paper that assessed how such assumptions can go wrong. This study aims to statistically analyze the compressive strength of concrete. The research involves generating a random data set of compressive strength values, they generated using MATLAB, which is then analyzed to determine the optimal number of samples required for testing. The study explores the relationship between the number of samples and the failure percentage in terms of compressive strength. They use hypothesis testing to compare sample groups against the population. Let's see some inferences from this research paper. This graph illustrates the percentage difference between the characteristic compressive strength FCK and the minimum value of individual test results for different grades. They have taken the grades of concrete from M15 to M60. The graph shows that as the grade of concrete increases, the percentage difference between compressive strength and the minimum test result decreases. This indicates that higher grade concrete tends to have test results closer to their characteristic strength, suggesting better consistency in quality. Okay, so when you go for higher grade, you will get good consistency. This is the one inference. This is another inference. This graph depicts the percentage difference between the characteristic compressive strength and the mean compressive strength of all samples for different grades of concrete. This graph shows a similar trend to the previous one, with a higher grade concrete exhibiting smaller percentage differences. This reinforces the idea that higher grade concrete is more consistent in meeting the required strength criteria. Okay, let's take another graph. This graph shows the distribution of 100 randomly generated compressive strength values for M30 grade concrete. The smooth bell-shaped curve indicates that the data follows a normal distribution. This is the key assumption in many statistical analysis, right? This normal distribution allows for the application of statistical tools like hypothesis testing to evaluate the compressive strength of concrete. Fine. This is another. What we receive from this graph. Number of specimen versus percentage. This is actually plots the percentage of samples failing the hypothesis test against the number of specimens in each sample. The graph clearly shows that as the number of specimens decreases, the percentage of samples failing the hypothesis test increases. This suggests that smaller sample sizes are less reliable in representing the population, leading to higher rejection rates, even when the concrete meets the required strength criteria. This is the underlying fact. So this finding underscores the importance of using an adequate number of samples in compressive strength testing to ensure accurate and reliable results. This analysis also highlights the limitations of the current codal provisions, which often result in the rejection of concrete mixtures even when their compressive strength exceeds the characteristic strength. To conclude, this study reaffirms the critical importance of aligning both codal provisions and robust statistical methodologies in evaluating concrete strength. While codes like IS 456 provide structured guidance, field realities often demand data-driven decisions, especially on large-scale or high-risk projects. Tools such as rebound hammer test offer reliable, non-destructive insights during ongoing construction, but must be applied judiciously. Moreover, calculating standard deviation on site rather than depending on assumed values enhances the accuracy of assessments and reduces the risk of unjustified rejections. Ultimately, a harmonized approach where statistical rigor and codal compliance go hand in hand lead to more reliable concrete evaluation, better decision making, and most importantly, safer, more durable structures. If you found this analysis valuable, don't forget to like, share, and subscribe for more insight on construction quality, analytics, and practical engineering applications. Thanks for watching. you.